In this video, we're going to focus on the RC bandpass filter. Now, before we design the circuit for that, we need to talk about the high-pass RC circuit and the low-pass RC filter. So this particular circuit here is a high-pass RC circuit. The high frequencies will flow right through the capacitor, but the capacitor will block the low frequencies. So that's a high-pass filter right there. And the frequency response for that looks like this. Now, for the low-pass filter, we need to switch the resistor and the capacitor. So we have a circuit that looks like this. Now, the high-frequency signals will flow through the capacitor, going back to ground. So it's going to be filtered out by the capacitor. The low-frequency signals will flow to the output. So that is a low-pass filter. And the frequency response for that looks like this. So this would be the cutoff frequency, where the output voltage is 70.7% of the input voltage. And here is the cutoff frequency for the low-pass filter. The formula is the same. It's 1 over 2 pi RC. Now, what happens if we combine these two circuits? If we combine them, we're going to get something known as a bandpass filter. So let's go ahead and do that. So that's the first stage, and here is the second stage. So we're going to call this C1 and R1. This is going to be R2 and C2. So now let's graph the frequency response for this type of circuit. So in the first stage, we have a high-pass filter, which has a frequency response that looks like this. And in the second stage, we have a low-pass filter, which has a frequency response. Let me use a different color. That looks like that. So if we combine the graph, we're going to get something that looks like this. So this would be the cutoff frequency for the high-pass filter. Let's call that F1 because it correlates to C1 and R1. And over here somewhere would be the cutoff frequency of the low-pass filter, F2, which corresponds to R2 and C2. Now the gain decreases by 3 decibels between the maximum level and the cutoff frequency. FR is the resonant frequency, also called the center frequency. The resonant frequency is the geometric mean between F1 and F2. The bandwidth is the difference between F1 and F2. So BW is equal to F2 minus F1. To calculate F1, it's going to be 1 over 2 pi R1C1. And to calculate the second cutoff frequency, it's 1 over 2 pi R2C2. So let's talk about the bandpass filter and how the circuit removes certain frequencies while allowing others to pass through. So the low frequencies are blocked by C1. Capacitors block low frequency signals, but they allow high frequency signals to pass through. So the high frequency signal will pass through C1 and also the mid-level signals, which we'll call FM. Now, the high frequency signals will be sent to ground by C2 because the capacitive reactance will be low, allowing the mid-level frequencies to go to the output. So that's why the bandpass filter works this way. It blocks the low frequency signals and the high frequency signals, allowing the mid-level signals to make it through the output. And we could design the circuit in such a way that we can select what center frequency we want and what bandwidth we wish to have. And we're going to go over some example problems on how to do that. So let's start with this problem. Calculate the resonant frequency and bandwidth of the RC bandpass filter shown below. So let's begin by calculating the cutoff frequencies. F1 is going to be 1 over 2 pi R1C1. So in this example, we can see that R1 is a 3 kilo ohm resistor, so that's 3 times 10 to the 3, and C1 is 20 nanofarads. Nano is 10 to the minus 9. So this is going to be 2652.6 hertz. So we can round that and say that's about 2.65 kilohertz. So now let's calculate F2. So that's going to be 1 over 2 pi R2 C2. R2 is a 2 kilo ohm resistor. C2 is 15 nanofarads. So this is going to be 5,305 hertz. So we could say that that's approximately 5.3 kilohertz. So now that we have F2 and F1, we can calculate the bandwidth. The bandwidth is F2 minus F1. So that's going to be 2.65 kilohertz. So now we can calculate the resonant frequency. So it's going to be the geometric mean of F1 and F2. So it's the square root of 5.3 times 2.65. And so the resonant frequency for this particular bandpass filter is 3.75 kilohertz. Now this is different than the average frequency. If we were to take the arithmetic mean, if we were to add up F1 and F2 and divide it by 2, this would be, let's see, 2.65 plus 5.3, that's 7.95 divided by 2. The average frequency is 3.975. It's not the same as the resonant frequency. However, it's pretty close. And it turns out that as the bandwidth decreases, the resonant frequency approaches the average frequency. But these are the answers for this problem. Here's another problem. Using two 5K resistors, design a RC bandpass filter with cutoff frequencies 9 kHz and 11 kHz, and calculate the resonant frequency and bandwidth of this filter. So the circuit that we're going to draw is going to be the same. The only thing that's different will be the values of the elements in the circuit. Now, we know the values of R1 and R2, so those are 5K resistors. What we don't know are the values of C1 and C2, and that's what we need to calculate. C1 is going to be 1 over 2 pi F1 times R1. Now, F1 is going to be the smaller of the two frequencies. F2 is the larger one. So this is going to be 1 over 2 pi times 9 kilohertz. That's 9 times 10 to the 3. And then R1 is 5 kilo ohms, so 5 times 10 to the 3. And so you should get 3.54 times 10 to the minus 9 farads. 10 to the minus 9 farads is basically a nanofarad. So this is 3.54 nanofarads. So that's our value for C1. Now to calculate the value of C2, it's going to be 1 over 2 pi F2 R2. So F2 is 11, R2 is the same. F2 is 11 kilohertz, so that's 11 times 10 to the third. And so this is going to be 2.89 times 10 to the minus 9 farads, or 2.89 nanofarads. So these are the values of C1 and C2 that we need in order to create a bandpass filter with cutoff frequencies 9 kilohertz and 11 kilohertz. Now let's calculate the bandwidth. So the bandwidth is going to be the difference between the two frequencies. So 11 minus 9, that's going to be 2 kilohertz. And the resonant frequency is going to be the square root of 9 times 11. So that's the square root of 99, which is 9.95. Notice that the average frequency of the two cutoff frequencies is 10 kilohertz. Since the bandwidth is relatively small, you can see that the resonant frequency is close to the average frequency. Here's another problem. Using two 10K resistors, design a RC bandpass filter with a resonant frequency of 6 kilohertz and a bandwidth of 9 kilohertz. So this one is different from the last problem. The last problem gave us the two cutoff frequencies. This one, it doesn't give us that. We got to find the two cutoff frequencies. Now, in the last problem, we saw that the bandwidth was 2 kilohertz and the resonant frequency was 10. The bandwidth was significantly smaller than the resonant frequency. And when that happens, the resonant frequency is approximately equal to the average frequency when the bandwidth is very small. In this example, the bandwidth is significantly larger than the resonant frequency. Because the bandwidth is so high, the resonant frequency will not be a good approximation, or rather the average frequency will not be a good approximation of the resonant frequency. And we'll see that in this example. But first, how do we use the resonant frequency and the bandwidth to get F1 and F2? Well, let's write down the two equations that we know. The resonant frequency is the square root of F1 times F2, and the bandwidth is F2 minus F1. We have two equations and two missing variables, which means we can solve this. So let's replace BW with 9. If we add F1 to both sides, we could say that 9 plus F1 is equal to F2. For some reason I put 92. So what we can do is solve this by substitution. We can replace F2 with 9 plus F1. And we can replace FR with 6. So we have 6 is equal to the square root of F1 times 9 plus F1. So now we got to do some algebra here. Taking the square of both sides, 6 squared is 36. And when we square the square root, we're going to get F1 and then 9 plus F1. Distributing F1, we have 36 is equal to 9F1 plus F1 squared. So moving the 36 to the other side, we have F1 squared plus 9F1 minus 36. In order to calculate F1, we need to factor. What two numbers that multiply to negative 36 add up to positive 9? Those two numbers are 12 and 3. Positive 12 and negative 3. 12 times negative 3 is negative 36, but 12 plus negative 3 is positive 9. So we can factor it like this. It's going to be F1 plus 12 and F1 minus 3. Now we can set each factor equal to 0. F1 plus 12 is equal to 0, and F1 minus 3 is equal to 0. So here F1 is negative 12, here F1 is positive 3. Now the frequency can't be negative, so F1 must be positive 3. So let me just rewrite this answer. So now that we have F1, we can calculate F2 using that formula. So F2 is going to be 9 plus 3, which is 12. And now we can check our work. So the bandwidth is F2 minus F1. 12 minus 3 is 9. And the resonant frequency is the square root of 3 and 12. 3 times 12 is 36. The square root of 36 is 6. So we have the right numbers. Now, if we were to get the average of these two frequencies, 3 plus 12 divided by 2, that will be 15 divided by 2, which is 7.5. So we could see a significant difference between the average frequency and the resonant frequency. And the reason why it's so different is because the bandwidth is so high. It's much higher than the resonant frequency. So now let's determine the capacitors that we need to use. But let's draw the circuit first. So R1 and R2, they're both 10K. But let's calculate C1 and C2. So C1 is going to be 1 over 2 pi F1 times R1. So F1 is 3 kilohertz. That's 3 times 10 to the third, or 3,000. And F2 is 12,000. That should be R1, not F2. R1 is 10K, or 10,000. So this is 5.3 times 10 to the minus 9, or 5.3 nanofarads. So that's C1. Now let's calculate C2. So we're going to use the 12 kilohertz signal. So that's going to be 12,000. So it should be 4 times less than the 5.3 nanofarad capacitor. And so you should get 1.33 nanofarads. So those are the values of C1 and C2 that we need in order to construct a bandpass filter with a resonant frequency of 6 kilohertz and a bandwidth of 9 kilohertz. Now let's try this one. It's very similar to the last problem, but this time the bandwidth is much smaller than the resonant frequency. And because of that, the average frequency will be approximately equal to the resonant frequency. So we don't have to solve by substitution or factor in order to get the resonant frequency. If we were to draw a graph of the bandwidth and the two cutoff frequencies, the center frequency is 6 kilohertz and the bandwidth is 0.4. So that means that the cutoff frequencies must be 5.8 and 6.2 to give us a bandwidth of 0.4. So this is a case where you could use the bandwidth to calculate the cutoff frequencies. All you got to do is start with the resonant frequency and add 1/2 of the bandwidth to get the upper amount, which will be 6.2, and then subtract from the resonance frequency 1/2 of the bandwidth to get the lower amount. Now we can make sure that these are the right answers by checking our work using this formula. The resonant frequency is the square root of f1 times f2. And so if we take the square root of 5.8 times 6.2, it will give us 5.997, which is approximately close to 6. So this is a good approximation of the cutoff frequencies. And so when the bandwidth is small, you can easily determine the cutoff frequencies. The average and the resonant frequency will be approximately the same. We couldn't do that in the last problem, where we had 9 kilohertz as a bandwidth. We couldn't say that the cutoff frequency would be 6 plus 1/2 times 9. That would be 10.5, which is different than 12. And we couldn't say that the lower cutoff frequency was 6 minus 1/2 times 9, because that would be 1.5, which is very far from 3 kilohertz. So this technique works if the bandwidth is very small relative to the resonant frequency. Now let's finish the problem. So let's determine the values of C1 and C2. So F1 is 5800 hertz, R1 is 10,000 ohms or 10 kilo ohms. So the value for C1 that we need is a 2.74 nanofarad capacitor. Now, let's find the value of the second capacitor, which shouldn't be too far away from the first one. So this is going to be 6,200 instead of 5,800. And so this is going to be 2.567 nanofarads. So those are the capacitors we need in order to create a bandpass filter with these characteristics. The only problem is it's very hard to find capacitors that have such precision in terms of their value. So that's the only issue with this. But theoretically speaking, if you can get these two capacitors, then you can create a bandpass filter with these characteristics. Now the reason why the capacitors are so similar in value is because we're using two similar resistors. If we decrease the value of one of the resistors, the required capacitor will increase in value. So let's focus on C2. So let's make R2 equal to 1 kilo ohm as opposed to 10 kilo ohms. If we do that, if we decrease R2 by a factor of 10, C2 is going to increase by a factor of 10 to give us the same frequency. So C2 is going to be 25.67 nanofarads as opposed to 2.5 0.67. So in this case, it will be easier to find a 2.7 nanofarad capacitor and a 25.67 nanofarad capacitor. So all you got to do is adjust one of the resistor values, and you could get significantly different capacitor values, which will make it a lot easier to create this circuit. So that's it for this video. That's all I got. Thanks for watching, and don't forget to subscribe.